Hello, my name is FLORESTELLA Rivera, and I am part of Dr. Sue Ann Chu's lab in the Department of Biomedical Sciences at UTRGV. And today my presentation will focus on the electrospraying of minocycline and temozolomide-loaded PLGA microparticles with PEG for the treatment of glioblastoma. Glioblastoma multiforme, or GBM, is an aggressive and common malignant brain tumor that causes angiogenesis, which is the tumor's ability to form new blood vessels, supplying it with the nutrients to keep growing. And because of this, the average survival for GBM is of 12 to 18 months post-diagnosis. Therefore, new treatment is necessary. Minocycline, a tetracycline derivative, has angiogenic properties that inhibit tumor growth, and temozolomide, an alkylating antineoplastic, is currently the first-choice chemotherapy drug for GBM. Polylacticoglycolic acid, known as PLGA, can help encapsulate these drugs, since it's a biodegradable and biocompatible polymer that has been approved for different drug delivery applications by the FDA. This study aims to fabricate electrosprayed minocycline and TMC-loaded microparticles with optimal morphology, drug loading, loading efficiency, release kinetics, and that they have the ability to kill GBM cells. We hypothesize that adjusting electrospraying parameters such as drug concentration and the addition of polyethylene glycol, also known as PEG, will impact these key properties, enhancing the effectiveness of the microparticles. As for methodology, in Figure 1 is a schematic of the electrospraying setup which is employed to fabricate the microparticles. The process begins by loading the polymer and drug solutions into a glass syringe. Then this is connected to a pump and a voltage source. The voltage for mino is 14 kilovolts and the voltage for TMC is 10 kilovolts. Then the solution is sprayed into a collection plate, and afterwards the microparticles are freezed and lyophilized for 24 hours. The drug loading, loading efficiency, and release kinetics are determined by absorbance. 350 nanometers for mino and 327 nanometers for TMC using a microplate reader. Another test is the MTT assay, which is conducted to evaluate metabolic activity, which reflects cell viability as seen in Figure 2. For the results, we're going to start with minocycline. In Figure 3, it's shown the SEM images of electrosprayed minocycline microparticles, and it can be seen how the microparticles containing PEG were found to be more aggregated than those without, like the 4.9 mino. Also, it can be seen that adding PEG and increasing minocycline concentration resulted in a more fused microparticle and greater aggregation, especially in the 12 mino PEG group. In Figures 4 and 5, the drug loading and drug efficiency tests were performed, comparing all the different types of microparticles fabricated. And as shown, the inclusion of PEG enhanced drug loading and efficiency by allowing more minocycline to be dissolved. A release kinetics test was done, and as shown in Figure 6, all microparticles groups exhibited a burst release of minocycline in the first hour, with the 12 mino PEG group showing significantly higher release than 4.9 mino group, from 1 hour to 7 days. Moving forward, the MTT assay was done using the 9.8 mg microcycline microparticles, since those were the ones that had the best morphology and they also had a consistent drug loading and release kinetics, by not being as high as 12 mg mino PEG or as low as 4.9 mg mino. So as shown in Figure 8, the MTT assay is comparing control, free drug, blank microparticles, and minocycline-loaded microparticles. And it's demonstrated that the blank microparticles did not harm the cells, but the drug-loaded microparticles caused significantly more cell death compared to the control and blank microparticles, showing that the cell viability reduced in the presence of minocycline. Now let's go to temozolomide. First, in Figure 9, TMC was exposed to two different spraying times, 4 versus 10 minutes, with a low chamber humidity. The results show that when shortening the spraying time and reducing chamber humidity, aggregation decreases and as a result makes drug collection easier. Moving forward, in Figures 11 and 12, drug loading and drug efficiency tests were done to obtain the proper solvent for TMC by comparing acetonitrile and dichloromethane. And as shown, using acetonitrile instead of dichloromethane as the solvent for TMC microparticles enhanced drug loading and efficiency due to the greater solubility of TMC in acetonitrile. Also, drug release studies were done, and in Figure 10, TMC had a burst release with 72.32% release within the first hour. Overall, it can be concluded that the 9.8 mg minocycline group combined with 3.5 mg of PEG demonstrated optimal morphology, high drug loading, and loading efficiency, as PEG allows more minocycline to be dissolved as seen in solubility study. It also was able to result in cell death compared to control and blank microparticles, making 9.8 an optimal microparticle minocycline. On the other hand, the 7 mg TMC microparticle group with acetonitrile yielded high drug loading and loading efficiency, since acetonitrile allows more temozolomide to be dissolved. Also, lower humidity levels in the spraying chamber were correlated with more spherical, less aggregated microparticles, which were easier to collect. And both types of microparticles resulted in a large burst release, but this can be decreased by incorporating the microparticles into a scaffold. Overall, electrospraying emerges as a promising method for the production of minocycline and temozolomide-loaded microparticles for the treatment of glioblastoma multiforme. Future research will focus on the efficiency of these microparticles in inducing GBM cell death, and on the integration of these microparticles into an injectable alginate scaffold to extend drug release. We acknowledge the support from the NIH Support of Competitive Research and the Research Continuance Award. Thank you so much.